Number one, closure. So let's say we have two orthogonal matrices, say O1 and O2. When we matrix multiply them, we get another matrix, say O3. So if O1 and O2 are orthogonal, is O3 orthogonal, right? That's the question. So let's see. O3 transpose O3. We want to show that this is the identity. So O3 is O1 times O2. So we have transpose here, O1, O2. So by the rule of transposition, we get O2 transpose O1 transpose, because when we take the bracket away, we have to reverse the ordering, then O times O2. But, matrix multiplication, like group multiplication, is associative. So we can associate these two guys, but they are orthogonal matrices. So we get O2 transpose times identity O2. And then, because this is also orthogonal, we have the identity. So yes, if O1 and O2 are orthogonal, we see that O3 is also orthogonal, right? Okay. Number two is the identity. So the identity here is obviously 1. Now, is that an orthogonal matrix? Well, the identity, if I transpose it, I get the identity, which is equal to the inverse of the identity. So yes, it is an orthogonal matrix. Okay. And of course, O inverse is O transpose. So yeah, the identity, the inverse exists. And associativity just follows from the fact that we have matrix multiplication is associative, right? So we have shown that O3 is indeed a group. Are there any questions? Okay, let me
I
make
don't
some
really get the
comments then.
argument why O inverse is in O3.
Why O inverse is in O3? Because O transpose is in O3.
I mean, I can say it's true, but it's not immediately obvious to me.
Oh, yeah. I mean, okay, one of the, are you saying that O transpose O is 1? And how does that imply this?
Yeah, I mean, we know that O is in O3, then how does it imply that O transpose is in O3?
Oh, right. Yes, sure. Yeah. If O is in O3, so let's look at O transpose and look at O transpose O. So if I do this, then I get O transpose, but it's a normal matrix, so it means that this is actually true. Okay.
Yeah, makes sense now.
Yeah. So yeah, I didn't show that, this was, because the left inverse is going to be equal to the right inverse by the argument that we saw earlier in the group class anyway, right? Okay, any other questions? Okay, let me make some comments then. The rotation in 3D is a subgroup of O3. Okay, so like note that we have O transpose O is equals to 1. Now, if I take the determinant of this equation, I just get this. Now, the determinant of a matrix doesn't change under transposition. So this means the left-hand side is the determinant of the matrix squared, and the right-hand side is 1. So this means that this equation implies that the determinant of O is plus or minus 1. Okay, and at some point we will show that you know, the subset of O3, you know, with the determinant condition O equals to plus 1 form a subgroup you know, which we call SO3. S stands for special, so this condition is called special. So these this subgroup represent rotations in three-dimensional Euclidean space. So as you know, the rotation does not change the length of a position vector, right? So of course it makes sense that rotation would be part of O3. But what it seems a little mysterious that rotations are correspond to a subgroup. And we will explore this further, but let me just make a few comments here. Number 2 is that the elements of O3, say with determinant -1, correspond to, say, discrete transformations such as reflection or parity. Okay, for example, if I take the matrix, say, P, which is one of a particular orthogonal matrix of the form -1, -1, -1, then this is called, you know, this is called parity. And what it does is that it takes a left-handed, you know, coordinate system into a right-handed one, right? So if you apply this matrix on all the unit vectors of your, say, your XYZ system, then you will have something else which is more like, you know, Z goes here and X goes that way and Y goes that way, right? Which then you can again, you can rotate, and if you rotate this, say, around the Y-axis, then Z goes up this way and Y goes this way. and X goes this way. And as you can see, this cannot be rotated into this, right? So there is no rotation connecting these two. So this is a left-handed, I think this is a left-handed, right? No, this is a right-handed, sorry. This is a right-handed coordinate system, and this is a left-handed coordinate system. So this is an example of an element of O3 that is not a rotation. And such elements of O3 they are discrete transformation. They cannot be written as rotations. Okay, that's comment number 2. We will get into, I want to discuss this in more details down the line. But if you have any questions, I can entertain them.
Sir,
yeah.
So the elements that are outside of SO3, is there any kind of interpretation of them as rotations, or are they different things?
Yeah, they're different things. They are essentially reflections of the mirror. They can involve rotation, but they always involve reflection. So for example, if you take the element, say, -1, 1, 1, right? So that just reflects in one of the directions, right? Which is basically what we do in the mirror, right? But this can be written as some rotation and some parity. Okay,
I was referring to like determinant greater than 1 or something. So that would be like a scale in addition to a rotation or something.
Exactly. That would take you outside O3 because you'd be scaling, right? Because if you're zooming in, you're no longer preserving the length of the vector.
Yeah, I see.
So, all of these, the O3, O3 sits inside GL3R, right? And GL3R has how many dimensions? How many parameter? What is the parameter space of GL3R?
9.
Right, so 9 parameter. So we'll see that O3 has only 3 parameters. Okay. All right, so what are the number of parameters of O3? So, don't think that scaling is not important. Scaling is important. There is a bigger group than O3 for, say, 3 dimensions, which involves the scalings. So it turns out that for some physics theories, it's important to consider the group of transformations which doesn't preserve the length, but which preserves the angle between vectors. And such a group of transformation is called the conformal group. So for the conformal group, you can take a triangle and you can scale it to a bigger triangle, right? And that's also allowed. Not just that, conformal groups can be even more crazy, that you can take a triangle and you can turn that into some weird shape like this, but that these angles are the same as these angles, okay? All right, so if you ever study the formal aspects of quantum field theory, you will come across the conformal group.